Hey everybody, this is Ruben back again. We're going to talk about limits at infinity today, which can be a little bit crazy, but it's not too bad. First things first, let's get a little notation. So when we talk about a limit at infinity, what we're doing is we're taking the limit as x approaches positive infinity of f of x, or the limit as x approaches negative infinity of f of x. All right, and the question is does this equal a limit? All right, that's the real question. Now, I want to give you a couple of examples of functions where we take limits at infinity. So, for example, if I do, let's do 1 over x squared. If I'm going to take, let's just look at 1 over x squared. So I know it goes like that and like that. So this is going to be f of x equals 1 over x squared. Now, we say, let's change colors here. We say we're going to take the limit as x approaches infinity of 1 over x squared. Now, if you think about a fraction, and we're doing this at infinity, it's kind of a tug of war between the numerator and the denominator. And those of you that have had Algebra 2, all of you will hopefully remember from Algebra 2, let's try it that way, that if the degree of the denominator is greater than the degree of the numerator, then the limit as x goes to infinity is going to be 0. But again, we want to think about this algebraically, numerically, and graphically. All right, the algebraic way is that whole numerator thing. We could think about this as x gets bigger and bigger and bigger and bigger. The value, if we're thinking about it numerically, then the value of the fraction heads for 0. If we look at it graphically, look, as x heads towards positive infinity, this guy hugs 0, doesn't it? So that's relatively easy to see. Likewise, if I take the limit as x goes to negative infinity, now I'm sticking in huge negative numbers. I'm heading in this direction. Again, what I get, if I do, 1 over x squared, what I'm heading for is 0. Now, what about f of x equals, let's go e to the x, our good friend and our cornerstone of delicious mathematics, y equals e to the x. Now it should be obvious that if I take the limit as x approaches positive infinity of e to the x, all right, if I plug in bigger and bigger numbers, if I do this numerically, because there's no real algebraic way to think about this. There is, but it's unduly onerous, let's put it that way. Look at the function. Think about the numbers. E to the big numbers gets bigger and bigger and bigger. Therefore, this guy is positive infinity, or I could say does not exist, or I could use the empty set. All right. However, if I take the limit as x goes to negative infinity of e to the x, well, now if I put in negative numbers, I end up with 1 over e to that number, right? Just using the algebraic property of x to the negative a is 1 over x to the a. Again, it's algebra. I don't feel compelled to write that, so you should probably know that. But think about it this way. As I head for negative infinity, this guy has a tendency to wrap towards y equals 0. So this guy is 0. Okay, now that probably is making your spidey sense tingle a little bit. What do you notice about y equals 0 in both of these cases from your algebraic experience? Well, they're horizontal asymptotes. So what we have is a horizontal asymptote definition. I'm just going to cheat a little bit here and call asymptote definition, where if the limit as x goes to positive or negative infinity of f of x actually exists, if it equals a number, then this implies that, let's do, well, I don't want to use L, because that gets a little overused. Let's call this, if it equals a number a, then this implies that y equals a is a horizontal asymptote. So we have this wonderful little limit definition of horizontal asymptotes. Now, I'm going to put something in here, and then something algebraic from back in your Algebra 2 days, and then we're going to play with horizontal asymptotes that we've already dealt with in the past. I don't want you to reinvent the wheel, but I do, however, want your thinking to be more calculus-centric as opposed to Algebra 2-centric, if those are words. All right, first things first, let's look at this. I know that if I take the limit as x goes to positive or negative infinity of 1 over x to the r, okay? 1 over x to the r. This guy is always going to equal 0 so long as r is greater than 0. If r is less than 0, now I'm kicking the r back on top because remember 1 over x to the negative a is equal to x to the a. So if that number gets huge, right, if I flip this up and I let x get really big, then this thing's going to blow up. However, if r is greater than 0, this guy's always going to go to 0. 1 over, just think of your numbers. Even if it's teeny tiny, x to the 0.00001, well, remember, infinity is super patient and it gets really big. So it will eventually get so huge that this is equal to 0. Now, that said, I'm going to show you a robust proof of a certain limit that we already knew. If I take the limit as x approaches infinity of, let's go x cubed plus 5x minus 2 over 3x minus 2x cubed. Okay, now, remember, limits at infinity tie into horizontal asymptotes. So like I said, I don't want you to completely discard your understanding of horizontal asymptotes because if you recall, remember, if I have some rational function x, which is equal to p of x over q of x. Now we're going to do a little review here, just real quick. If the degree, we'll put it right here. If the degree of p is greater than the degree of q, this implies no horizontal asymptotes, right? If the degree of p is less than the degree of q, this implies y equals 0 is your horizontal asymptote. And last but not least, if the degree of p is equal to the degree of q, this implies y equals, oh, I didn't give myself enough room, ratio of lead coefficients. That may be off the screen a little bit, sorry about that, of lead coefficients. Again, review is your horizontal asymptote. All right, so looking at this, look at this. I've got the degree of the top, I've got the degree of the top is 3, the degree of the bottom is 3. So theoretically, according to our Algebra 2 definition of horizontal asymptotes, which I'm allowed to use because I'm taking a limit as x goes to infinity, our horizontal asymptote should be y equals negative 1/2 because the lead coefficient of this is 1, lead coefficient of this high degree is negative 2, so I should get y equals negative 1/2. However, I'm going to show you how to take this thing using actual robust limits, okay? So I got x cubed plus 5x minus 2 over 3x minus 2x cubed. All right, now remember, I'm allowed to multiply by a goofy looking 1 anytime I want, okay? And I'm going to multiply by a really goofy looking 1. So long as the 1 isn't dividing things by 0, we're in pretty good shape, okay? So I'm going to multiply by 1 over x cubed over 1 over x cubed. That's just a goofy looking 1, isn't it? So that should turn into the limit as x approaches infinity of, well, x cubed over, I'm multiplying this entire thing by 1 over x cubed and this entire thing by 1 over x cubed. So this should turn into x cubed over x cubed, which is 1, plus 5x over x cubed, which is 5 over x squared, don't know why it's doing that, minus 2 over x cubed, all over, and now I'm gonna have 3x over x cubed, which is 3 over x squared, minus 2, right? Everybody agrees? Because 2x cubed over x cubed is 2, right? And I've got the minus along for the ride. Now, be really, really careful with your limits. Remember, these limits are always along for the ride. I don't stop writing limit until I've taken the limit. Okay, now if I use this rule right here, wow, I don't know what happened there. If I use this rule right here, do you agree, well, hopefully you agree, that this becomes 0, this becomes 0, and this becomes 0. So the limit is equal to negative 1/2, which implies y equals negative 1/2 is my horizontal asymptote. Now remember, I'm tying in a whole bunch of things there. If I'd thrown this limit at you without giving you this horizontal asymptotic definition, you would be like, well, wait, why am I allowed to do that? Or why am I actually allowed to use these guys instead of this sort of long algebraic process? right? However, we know that as soon as I take a limit at positive or negative infinity, that, guess what? We're looking for horizontal asymptotes. Also, if I took the limit as x approached negative infinity, notice I would have gotten exactly the same thing by this rule, right? Negative infinity, this guy's going to 0. This guy's going to 0. This guy's going to 0. I'm still left with y equals negative 1/2. So I have this sort of robust algebraic process by which I can take a limit at infinity to prove the existence of a horizontal asymptote. However, if I know the horizontal asymptote already exists, I get the limit at infinity for nothing, right? Since from my Algebra 2 days, I already can look at this and know that the limit, and know that it has a horizontal asymptote of y equals negative 1/2 by virtue of these guys over here. So I know what the limit is for free. Now, the way that I've explained this in the past, and I like this explanation because it makes me happy, and that's all that really matters, is think of it as a tug of war, all right? If I have a tug of war at infinity, right, as in this case, at infinity, let me go to red again, at infinity, really 5 times x, and minus subtracting 2 from infinity, how frightening. Those guys don't really matter. So what I end up with is a tug of war between x cubed and negative 2x cubed. Well, in that tug of war at infinity, guess what? It's a tie. Now, that would deal with these guys. If it's a tie, then all that's left is the negative 1/2. Now, if I go to this guy, if the degree of the top is less than the degree of the bottom, then the bottom wins the tug of war. If in a fraction, the bottom is allowed to get bigger faster than the top, guess what? It goes to 0, right? Big numbers over huge numbers are 0. Likewise, if the numerator is allowed to range to infinity far more quickly than the denominator, well, huge numbers over big numbers equals huge numbers on top. Infinity on top wins. If infinity on the bottom wins, it goes to 0. If infinity on top wins, it goes to infinity. If there's a tie, it's just the ratio of the lead coefficients. Okay? Okay, there's one more thing that I want to talk about with you really quickly, and then just a couple of limits so that you don't get too crazy screwed up on this thing. I can put them right down here, and then I'm done for the section. Whoa, that's cool. I haven't seen that yet. Huh. All right, sorry. If I take this guy shows up from time to time. If I take the limit as x, you know what? I'm going to need more space for this. If I take the limit as x goes to infinity of, let's say, inverse tan of x. There's a couple of specialty functions I want to talk about. Well, hopefully you recall from back in the day that the inverse tan of x looks like this. Remember, it's the inverse function of tangent, right? So if I reverse the x and the y, I get this guy. If I reverse the x and the y, I end up with this, right? And I already, wow, that's awful. Sorry, guys. I already know that inverse tan of x, by virtue of my trig training, has horizontal asymptotes at y equals pi halves, and y equals that's a y, by the way, not a g, and y equals negative pi halves, because tangent of x has vertical asymptotes at positive and negative pi halves. So you see what I'm trying to do here? Since I already know that these have horizontal asymptotes here and here, I get to use that information for nothing. Therefore, because of the link between limits at infinity and horizontal asymptotes, like, there's nothing to do. I know that the limit as x approaches infinity of inverse tan of x equals pi halves, because as I take off in this direction, inverse tan of x heads for pi halves. Likewise, I know that the limit as x approaches negative infinity of inverse tan of x, because as I go in this direction, the curve heads for negative pi halves. Now, what that should tell you, and that's really, really important, what it should tell you is, is that we're not necessarily always going to have the same limits at positive and negative infinity, right? We discussed that back here with e to the x. E to the x has no limit as x goes to infinity, and it's got 0 as x goes to negative infinity. However, I can have 2 different existing limits at positive and negative infinity. So don't just be like, oh, the limit as x goes to positive and negative infinity of inverse tan of x is pi halves, because you're wrong. The limit as x goes to infinity of inverse tan of x is pi halves, limit as x goes to infinity, x goes to negative infinity of inverse tan of x is negative pi halves. So be leery, pay attention, think graphically, think numerical, think algebraic. There's lots of different ways to skin a cat. In this way, we just use graphical analysis to determine, right? There's no algebra. I reckon we could have used numbers. We could have gotten out our calculators and started plugging in bigger and bigger and bigger numbers and seen that inverse tan heads for pi halves. Although, that's the crazy thing, is on our calculator, it's not going to write pi halves, is it? It's going to write this thing as a decimal, and we may not readily see that as pi halves or negative pi halves. Okay, however, you have all those tools available to you. All right, that's enough of me yapping at you. Hope you enjoyed the lecture, and I'll talk to you soon.